We used to have to convince our undergraduate students that geology had the potential to directly impact on one's life. And after 2010, it's not as tough of a sell for us. So I just want to briefly run through some of the impacts of the Canterbury earthquake sequence. And the photos I want to kick things off with here basically show how geology can influence things at the surface by changing the position of the ground elevation, and the follow-on effects that sort of thing creates transcends any aspect of physical science. It directly affects people living there. It influences our underground networks in a variety of different ways, and it increases and highlights the decisions we've made and where we've chosen to live. So that's the point of my talk today. It's nice to know where we came from, and so this image here shows a background seismicity in the decade prior to 2010 in the Canterbury region. Each one of those pink dots represents a magnitude 3 earthquake. And as you can see, there was no real precursory evidence in the area that was to become the seismic hotbed. No earthquakes over that preceding decade there. However, there was, in the mid-90s, an analogous sequence to the one that we just experienced, a cluster of magnitude 6 earthquakes between 1994 and 1995. So there was clear evidence for a history of earthquake clustering in recent times. We also had a series of local earthquakes in 1869 and 1870. So we knew that we could get earthquakes locally. Despite that, there was somewhat of a NIMBY culture that persisted in Christchurch that influenced some of the decisions that we made. This is how the picture changed in the next 3 years. You can see, obviously, quite a strong contrast there between those two images. 30 kilometers north-south, 100 kilometers east-west. Other areas have had an increase in seismicity rate, showing us about the redistribution of stress throughout the crust. If we look at earthquakes, they are quite simple in their beauty and their distributions. This shows how, on a logarithmic plot, the number of magnitude earthquakes at different magnitudes. So for every magnitude 5 earthquake, we get 10 4s and 100 3s, and that's why we've had thousands of earthquakes for that simple relationship there. If we look at that plot in detail, between 2010 and 2012, we had 550 to 600 times the rate of earthquakes that we had in the preceding 70 years. At the moment, in 2015, we're about 30 to 35 times more the rate of earthquakes. So we're still at an elevated rate of seismicity in the area. Oh, sorry. This shows the gradual progression of the sequence. We had one surface rupture here on a whole network of faults, blind faults here. The red dots, you can see the dates here. The red dots were the early earthquakes, and the sequence migrated further and further to the east and offshore, each one of these being a blind fault that was not easily identifiable at the surface. So I just want to summarize some of the impacts of this. Obviously, surface rupture in the first earthquake impacted on agricultural land, impacted on people's houses. These are great success stories, the fact that an earthquake can rupture right through someone's house and no one can die. This is the beauty of modern, well-constructed houses. Impacted on lifelines, roads, power lines, etc. The earthquake had a major impact on surface water distributions. In this case, the fault rupture dropped one side of the land down and caused rivers to flow in directions that they had not flowed before. We also had a series of quite dramatic impacts on our forests in that region. The earthquake caused severe and recurrent liquefaction. In fact, the backyard of the property I used to live in liquefied 10 separate times during the earthquake sequence, and here's an example of what that looked like in different earthquakes. It also caused, in a lot of areas, severe lateral spreading, and those sort of effects directly informed where things like the red zone were drawn. If we track the elevation of the land surface through time, we see dramatic effects that have long-lived implications for how we look at Christchurch and Christchurch's future. So these are differential LiDAR images that just show the effect of the earthquake in terms of upward elevation changes versus downward elevation changes. And as you see, as I progress through this, this is the February 22nd earthquake. You can see parts of southern Christchurch and the Port Hills were uplifted, but large areas of Christchurch subsided as a result of both tectonic movement and subsidence. And as that series progresses, there's the June earthquake there, and there's the December earthquake there. So you can see vast amounts of eastern Christchurch here have subsided up to 0.5 meter and some places beyond. That has had implications on a variety of things, including flooding, as you can see in Bexley in this image here. We also had changes in the shape of the rivers. So because of lateral spreading, the rivers became narrower and the floodplains subsided, meaning that the rivers had less carrying capacity. So gravel levees were constructed to try to keep the rivers within their bank to the levels of what the land was prior to the earthquake sequence. But of course, there's been follow-on issues with the amount of water that those rivers can handle. Estuary changes. The estuary actually has parts of the estuary have been uplifted and other parts have subsided, as you see there. And the response of vegetation throughout the region has also changed. So this is an area that used to be tidal. It's been uplifted, and we're seeing colonization of formal tidal flats with salt-tolerant vegetation. Quite dramatic examples of cliff recession and some evidence for bad choices. This is a photo of a cliff face after the Darfield earthquake and before the February 22nd earthquake. You can see there was a vacant lot there. Sometime after that, this lot was developed prior to the February 22nd earthquake, and then in the February 22nd earthquake, large rocks fell all around. If we'd given that a couple more months, there could have been people obviously living in there. And then this is an example of the importance of good field observations. This is a crack here that formed in the February 22nd earthquake, which then failed in the June 13th earthquake. So just to summarize some of the knowledge that has come out of the last few years, we have been studying liquefaction features in detailed detective work, and we find liquefaction occurs in eastern Christchurch on the order of hundreds of years, particularly susceptible sites very frequently. We think the Alpine Fault earthquakes can cause liquefaction in parts of Christchurch in the red zone. When we look at the return times of very severe rockfall, analogous to the February and June events, we think that they're telling us about thousands of years between successive major rockfall events like that. However, within those events, we have clusters of events, and that's one of the decisions, or one of the complicated issues of science. And finally, when we look at individual faults and their return times, we dig up the Greendale Fault, study the history of earthquakes on that fault. The last earthquake on the Greendale Fault was 25,000 years ago, plus or minus 3. So that thing sat around for a very long time before it ruptured beneath people's homes. So when I think of Christchurch, I see a land of great beauty, in part due to the earthquakes which have shaped our environment. I see a land of tough challenges and abundant opportunities. And as we go forward, I really am quite interested in this constantly evolving interface between science, policy, and community at all levels. Thank you very much.